If you've ever seen one of these signs and that sneaking voice in the back of your head has said, "Why is it so dangerous? What is voltage? Should I touch it?" Well, get ready, because you're in for a bit of a shock.
Do you feel the vibes?
All right, let's start this off with the basics. Voltage is the change in the electric potential. An electric potential is sort of like elevator music for the universe. We don't always notice it, but it's always there. We often just forget about it until it does something odd or really important.
Great. Stuck in an elevator with 5 guys on a high-protein diet.
In more technical terms, the electric potential is the amount of electric potential energy per unit charge at a certain point in space. This is often created by charged objects within the environment, creating an electric field, and therefore the potential for electric force, therefore potential for potential energy, right? Which is why we call it potential, because it's the potential for energy to be there. So basically the environment is like,
I look around this room and I see nothing but untapped potential. You have potential. You have... Oh boy.
so what does this really look like in terms that we can be more familiar with? Well, imagine this. You've got a charged particle, and depending on where you place it, it either feels really comfortable or super stressed out because of the electric field around it. The potential is the environment, and the environment with low potential is more comfortable for charges to be in. So they don't gain a lot of energy and don't really move around. They don't really want to leave quickly. So they just kind of stay there at a low velocity. But meanwhile, locations with high potential are relatively uncomfortable, and therefore they give a lot of energy to the particles and make them want to move around. Try to get to somewhere that is less stressful. Electric potential, represented by V, is typically in SI units of, well, also V, volts. Now, don't confuse this with potential difference, which is delta V, which we usually use when we talk about voltage. That's the difference in potential, which is what really makes things move. See, if everywhere is stressful, then there's nowhere you could go that would make it more comfortable. Therefore, you just stay where you are. Meanwhile, if there's a high potential difference or a high voltage, it's kind of like the difference between the top and bottom of a slide. Charges will go from the place of high potential to the place with lower potential. And so voltage is the reason that electrons move, just like gravity is the reason you go down the slide. Yes, it's a gravitational force that pulls you down, but really you could also look at it as the difference between the gravitational potential at the top and bottom of the slide, and the preference for objects to move from high potential to low potential. Now, let's look at what this potential energy looks like for a point charge in your environment. The electric potential V, due to a point charge Q, would look a lot like the potential energy in that area, but missing one of the charges in the numerator. So it would be given by KQ over R. That means that the closer you are to the charge, the higher the electric potential. And if you get too close, this is because the potential difference is so high between the charge and you, who would be grounded in this case, so you have a potential of 0, that the charges will move even through air, which is a good insulator, and out of the charge that they were originally in. This is a process that we call arcing. So remember, the electric potential depends on how far away you are from the source of charge. It's like trying to avoid that one friend who always brings way too much drama.
I can't go to Taco Bell. I'm on an all-carb diet. God, Karen, you are so stupid.
The further you are from them, the less frustrating it is. And when your friend who has no drama shows up, you just immediately cling to them like they're your only lifeline. So, as we've discussed, charges naturally move from areas of high potential to low potential, just like how whenever you're stressed or scared, you want to go somewhere that's a lot more comfortable. To judge where we have these regions of high or low potential, we can compare the potential difference and see how the charge will move. And in order to do that, we look at something called equipotential lines. These lines represent the locations of equal potential within the environment. So for a point charge, this would look like concentric rings around the point charge. And to move along one of these lines means that there would be no change in potential, so no change in the potential energy for a charge that moves along the line with a fixed charge. The charges will experience a force perpendicular to the line, since they'll want to move from the higher line to the lower line. And therefore we can see that the E field would always be perpendicular to an equipotential line. Electric potential is relatively easy to measure, since we just measure the potential energy for an electron at a location and compare it to the ground, which would always have a potential of 0. This tells us that the potential difference between that point and 0, which would just be the potential at that point. So this would be what it means when you see a sign that says high voltage, or when you read the 120 volts that's found in a standard outlet. This potential that's listed and measured is the potential supplied by that outlet and will cause the movement of the electrons in the metal conductors that we plug into them. And the electric movement is what we call electric current. This is how we power everything from your phone to the fridge, whatever. And that's it. I guess we've exhausted our potential here. Don't forget to like, comment, and subscribe on this video.